Okay, so let's get started again. So Shiry wanted me to mention, by the way, that we do have a theme to each day. So if you're wondering, why is it all vision today? Today is the visual perception theme. And then tomorrow will be learning. And then we'll have physical and causal reasoning, understanding. On Wednesday, auditory learning. On Thursday, and on Friday, sensory motor. So we're covering a whole bunch of things. They're all kind of low level. The second workshop later will be more cognition and reasoning. And okay, so now we get to have our wonderful main organizer and host, Shiry, as the next speaker. And I just wanted to say that even though there's a bunch of us listed as organizing, I'm listed as some chair of this workshop, it's really all Shiry. Like this whole thing is due to Shiry, so we should really thank her for that. Okay. So we're all here because of you, so let's hear Shiry's talk.
Thank you. I mean, the truth is that that's kind of true. But then again, when we both came to the Simons here and we proposed this program, Shafi, I think you're not here this week, but she looked at us. Well, we had our proposal or whatever, and then she looked at us and she's like, all these people that are on your list, are they actually coming? And I was like, yes. And she's like, Christos is coming? Yes. Antonio Torralba is coming? Yes. Of course, I didn't know that they were coming. I was just like bluffing at that point, right? But she was like, okay. So that's how we got in. So it's me, but it's all of you who agreed to show up. The other thing I have to say is that this was supposed to be Jim DiCarlo, the second talk of the day, but he had to be otherwise engaged. And so instead, you get me. All right. So my question today is about visual perception and visual prediction. And what are the representations that enable it? But let's start from the very beginning. In the very beginning, living things on Earth were mostly stationary, and they didn't have eyes. But then something magical happened around the Cambrian period, when suddenly both eyes and fins were invented. And from then on, most of the creatures that evolved could both move and see. And the question is why? So if you ask Gibson, perhaps seeing and moving are intertwined. There's no reason to see if you can't move, and vice versa. But I think that's not the full story, and really we also see in order to predict how other folks are going to move. Because of course the problem with having everybody moving is that everybody is moving, including whomever you're trying to eat. So vision becomes a tool for behavior prediction. Now we know that predictions are a core aspect of our neural processing, but I don't think we know how they're actually implemented in the brain and what representations they lead to. So what is the visual representation that enables this prediction? What is the visual token that we predict? In language, predictive models have been a huge success story, and a big part of this success is the use of discrete word tokens. So a large language transformer like GPT takes as input a prefix of words as context, and then it can autoregressively predict the next word in the sequence. But what should a visual prediction token be? We can think of a whole spectrum of possible options that lie between low-level and high-level representations. On the far left, we have something like pixels, which is the most unstructured raw bit of visual information that we might be able to use. And on the opposite end of the spectrum, we can think of something like objects, like 3D objects that operate directly in the world. But before we pick our poison, we have to take into account another set of consideration, which has to do with the fact that imposing more physical object level priors is going to make our lives easier in learning to predict, because we're going to have to use less data and less compute. So why don't we try and predict in this cheaper space of 3D models? And indeed, in cases in which we have such 3D models, this is a fantastic idea. So for humans, we now have 3D parametric morphable models that you can use off the shelf and that disentangle the human form into shape, joint rotations, and mesh parameters. And this low-dimensional set of parameters represents all the people in all physically plausible poses. So we can just predict these parameters, which is cheap, easy, and will not violate physical constraints. And if you know a little bit about my work, I've been playing in this field for a very, very long time. And the way that we do this is that now we even have the technology to infer these 3D models of people directly from video. So given a video in the top left here, we can automatically reconstruct the 3D models of all the people in the scene. And this is work from Berkeley. You can talk to Ditendra, you can talk to Jorgis about this. So what kind of prediction can we do with this? For example, here's a project we're working on now where we're looking at videos of swing dance. And what I'm doing here is I'm going to take one dancer, let's call them Bob, as input, and I want to predict their partner Alice. So in this case, it's a mass prediction. I'm not predicting the future, I'm predicting one person from the other. And as I said, I can do this directly from video. So here on the top left is the ground truth video. In blue is going to be the input person, Bob, and in pink is the ground truth output person, Alice. Once we start predicting, you'll see Alice in yellow. Okay, so for humans, since we already have this 3D parametric representation, it's a great idea to use it for prediction. It's cheap, it doesn't require a lot of data, we can do this in academia, everybody's happy. But we really only have these parametric models for humans because we cared enough about people to go through the very expensive process of creating them to begin with. To get where we are with humans, required thousands of 3D body scans in the lab. What about everything else in the world that we can't possibly 3D scan and we don't have models for? All right, so how about we bite the bullet and just predict raw pixels? Indeed, initially folks tried to predict pixels, but it turns out that predicting pixels directly in future frames on video is really, really challenging because the problem is ambiguous and the prediction averages together possible futures into a single blurry prediction. So to mitigate this, there is all kinds of ideas, and here's an example from Sergey Levin, 2018 here at Berkeley, where they proposed to add a variational model and an adversarial loss or a GAN on top of this. And the kind of results that they get, where here the predicted frames are in yellow, is something like this. And you can see that this is a hard uphill battle. Working with raw pixels doesn't impose any physical priors on the prediction process. And so to learn how real objects behave in the real world, we would need to use a lot more data and a lot more compute. So what should we do? Well, what if we go a little bit more structured and take the dynamics of the pixels into account? So consider these collections of 2D points. When they're static, they kind of look like random collections. But when there is motion, the human brain sees 3D in these tracks. So what is this person doing? Can you see it? Walking. Thank you. And this person here? Biking. There you go. So tracking 2D points and predicting in this space might be a good idea. And thanks to Andrew Zisman here somewhere, we now have technology to track any 2D point in video. And this is a great example from DeepMind, where there's no prediction of future here. This is literally just tracking points in the video. It's a system that learned to do that for any input video. So now we can use these tracks as training data, such that given a single image, you could learn a model that would predict the future dynamics of points on the image. And then you can do a simple version of video prediction by morphing the original image according to the dynamics that you learned, and you then fill in the holes. Okay, so it's okay, but it kind of gets weird when things start occluding one another. And that makes sense because during occlusions, these 2D points, they just disappear. They don't have enough information about the structure of the object itself in 3D space. Okay, let's go a little bit more structured, and let's agree to pay the price for image patches. Because I know what you've been thinking all this time. You've been thinking, come on, I wasn't asleep all this past year. Sora already solved this, right? Well, let me give you a hint. I actually think that if you really look at the geometry here, it is completely wacko. It is not realistic at all. But how does Sora work? Well, in essence, where LLMs have text tokens, Sora has visual patches. At a high level, they take videos, they turn them into patches by first compressing them into a lower dimensional latent space, and then decomposing the representation into these space-time patches. So the prediction happens with these latent 2D temporal patches. But with all the data and all the compute that OpenAI threw at this problem, it still doesn't really work much of the time, because there's nothing here that is forced to respect physical priors. And learning these priors end-to-end from data, if it's even possible in practice, is prohibitively expensive. So what do I really want? Well, it turns out that what I really want, Ted Edelson already wanted in 1994, which is a lot of the time the usual case. Back then, Wang and Edelson described the problem of an object like a hand that's moving independently from a background that is also moving. And what they were after was a layered video representation that could represent these independent motions and be kind of a coding system for video. And it turns out that we're still working on the same problems today, but with very different technology. So what tools do we have now in our arsenal that we didn't have back then? Well, we have friends from graphics. And in graphics, there's been a huge surge of activity in 3D reconstruction techniques such as NERF for reconstructing single scenes through optimization. So the setting here is that you have some scene and you have multiple images of that scene from many different viewpoints. And using these different viewpoints, you can estimate the 3D structure of the scene and optimize the resulting 3D shape to fit the real object by projecting back, like taking a picture to the 2D image of what it might look like from each of these cameras. And then you can use the real image from that camera as an optimization target. So once you estimate the 3D scene, you can synthesize an image of it from any novel viewpoint. One of the most recent proposals of what the optimized 3D shape should consist of is to use a collection of 3D Gaussians that could be any location, size, color, and opacity. So for example, given this input scene, let's say you had pictures of it all around, the optimization might result in this collection of Gaussians, where here I'm only showing their centers. The really nice thing about these Gaussians that caught my eye initially is that they are dynamically distributed such that they concentrate in areas of higher visual frequency that usually correspond to the objects in the scene. So here is what these Gaussians look like when they're all plotted together, completely opaque. And when they're blended together with the opacity parameter that is also optimized, you get a really good reconstruction of the original scene. And then we can afterwards synthesize how the same scene would look like from any direction. Okay, so this is graphics, but because this is optimized only for this one scene, it only works for this particular scene. So my question is, can we learn from many images to output this 3D Gaussian reconstruction for any image? So what I'm proposing is to move yet a little bit more towards the structured direction and learn a 3D-ish representation based on Gaussians across scenes. This could be a nice mid-level representation for images that will enable video prediction while respecting the physical priors of objects that are moving in the 3D world. So this is exactly what we did, where you can think of the term Gaussian splatting as simply meaning 3D reconstruction with Gaussians and masked autoencoders as a technique for learning in a self-supervised way across many images. And this is instead of the original optimization set up for a single scene. Now, this work was led by Jathajan, who I think is not awake yet, but he will show up later, and you can ask him all the nitty-gritties of this method. How do we learn this representation? Well, let's start for a second by talking about masked autoencoding, which is a self-supervised image representation learning approach. So given an image, we split it into patches. We mask many of these patches, And then we feed the visible patches into an encoder to get their latent representation. Then we combine this representation with query tokens for the masked parts of the image. And from this, the decoder's task is to reconstruct the original image. Like any other autoencoder, all of this can be trained end-to-end in a self-supervised way using an image reconstruction loss. So what we do in our paper is to keep the self-supervised masked autoencoder setup, but instead of letting the decoder spit out pixels directly, we ask it to instead predict the parameters, so their location, scale, color, and alpha of a collection of 3D Gaussians. And then we can render these Gaussians back to the 2D image plane from the camera's point of view using the differential rendering operation of Gaussian splatting. So we're just really forcing the autoencoder to go through this mid-level representation of 3D Gaussians in the middle. In representation learning, we often evaluate what we call the image representation, which is the encoded latent from these visible patches. And so first of all, I want to assure you that in terms of representation learning, we don't lose anything by adding these Gaussians. On all the supervised image benchmarks, like classification, detection, and segmentation, we perform similarly to MAE. Even our training is just as fast as training the vanilla MAE. But what do we gain? Well, first of all, unlike masked autoencoders, our decoder model is fully decoupled from encoder tokens, so we can use any number of Gaussians for decoding. And it turns out that, like we want, the more Gaussians that we use, the better performance we get. But what is even more interesting is to look at this mid-level representation that we forced into the autoencoder. Because it learns grouping. The non-uniformity of the spatial organization of Gaussians leads to a spatial distribution of representational density that correlates with the information density in the image. By allowing the 3D Gaussians to move along the z-axis freely, our model learns some underlying structure of the natural world by observing not only the single viewpoint of one image, but millions of such single views. So as a result, we get out of the box figure ground segmentation, layering, and edge detection. How does this happen? Well, first of all, we saw that the Gaussians are dynamically distributed in the XY plane and concentrate around objects. They also tend to separate objects in the depth axis and represent them in distinct frequency layers. And this enables zero-shot foreground background segmentation and object detection. By splitting the layers into distinct levels and defining edges at places where there is a discontinuity from one level to the next, we can hierarchically find the edges in the image depending on how many levels we use. And naturally, the dynamically learned non-uniform distribution of Gaussians enables us to reconstruct high-frequency regions like lines and edges. So I think I can safely say that there is enough representational power here for prediction. And a learned representation with 3D Gaussians is a good candidate for a visual prediction token. Of course, the only questions that remain now are, can we actually make this work in video? And can it serve a model for prediction mechanisms in the brain as well? And this is to be determined. If there's updates in the next month, I will let you know. But I think I will stop here. And I even made it in my original time slot. Yes, okay, good. Yes, Pietro.
Very interesting work. I think it's a great idea. I'm curious whether you looked at the statistics of the images you use for training, because like the one here, you have depth from the focus as a cue, and often, so some data sets have that cue very strongly, like sports pictures and animal pictures, and some data sets like regular photos you take with a phone much less. So I'm curious if you looked into that. And
yes.
You see.
So this is currently trained on ImageNet because we want it to be, apples to apples with MAE. But right now, we're training this on kinetics, so we want to do this in video. And as you know, video frames are much more everywhere, right? They're much less structured. And it's performing very similarly in this single image scenario. I'm not showing it here because it's not polished yet, but it does very similar layering there as well. Yeah. Yes.
So with the video case, have you tried doing next token prediction rather than masked?
Yes. So I don't know that Justice Fund allows me to tell you what exactly we're trying to do because we are recorded and streamed, but we can talk about it privately later. Okay? Yes. Yes, because once it's working, I will. Yeah. Yes.
Gaussian splatting example you showed. Do you have an idea of like the complexity, and if not, like do you like doing that for a given scene, like sort of rotation if you showed the video? And if not, do you have like some just rough idea of how long it took to generate that video?
I do not. I wish. Is there a graphic, Aaron? Where's Aaron? Does Aaron know? No, I don't really work with nerfs and that sort of. Yeah. I don't really know. Yes.
No, much faster.
Much faster. Well, how? What is much faster?
The Gaussian splatting.
No, but he wants in general to know what's the complexity of this and how long it takes to do these things.
Like in woke, it's like it's slow real time. Like you can rotate things and basically in real time, but it's kind of slow.
Few seconds.
Less than that.
Less than that.
Yes.
Does the Gaussian representation also like help segregating multiple objects and overlapping objects?
Yes. It's just that so this is trained on ImageNet. We have other results in COCO, and with COCO segmentation, we get. Well, you have it before. We get similar things. What we do there is we trained on here on the right is COCO, object detection and segmentation, and in COCO is not just one image. Not just one object. It's multiple objects, and sometimes they're very, very small. And what we did is we trained the big model on ImageNet, and then we fine-tune it on COCO because these things are quite big. There's no reason to start from scratch. Yes.
I have two questions. First one is, what is your ground truth for the 3D like patches themselves? Because the ImageNet is you don't have the same object in different views, right? And then the second question is, what you mentioned is very interesting, right? That you have higher density of the Gaussians around, like for example, foreground object, which sounds very similar to what you see in DynoV2, when you do PCA on the features. So I wonder, like, what do you think is the core advantage? Is just that the Gaussians give you 3D, or that it's more performant, or because it seems that even in pixel models you already get kind of like this emergent features that you described.
Okay. So the first question is, where do we get 3D supervision? Because we don't have multiple pictures of the same object. We don't. You could dream that this would just work and give you 3D because it's seeing a lot of different objects in different viewports. It doesn't actually give you 3D, right? It gives you layering, but the layering has to do a little bit more with frequency than with actual depth. I think that's my hypothesis, right? Because really, there's no reason that you should be able to get 3D for free from single images. That would have been like a very surprising result, right? The advantage of using Gaussians will come in video, because once you have video, you actually have multiple views of a single object, right? And then if you can learn from the video to reconstruct the 3D in a self-supervised way, then you're done, right? So that's why we're going in this direction. It's not because of the single image case, but the single image case is kind of like a test bed to make sure that we're not losing anything by doing this. What was your second question? Your second what? I answered both, I think, right? Okay, Evan.
Yeah, it's really nice to see the variable computation of the number of Gaussians in the decoder. Is there a chance to make that adaptive? Like, could you do that as a function of the input? Because there's very complexity.
Yes. It's just for simplicity of experimentation, we did it this way. But yes, there's no reason why to not do it adaptive. And I think the original Gaussian splatting actually does that. They adaptively change the number of Gaussians. We're just lazy computer vision people, and there's a lot of Yeah. But yeah, absolutely. Yeah, it would work much better if it was. Yeah. Yes.
On the topic of getting 3D from these 2D images, do you find that regularizing things like the size of the Gaussians or some kind of smoothness between neighboring Gaussians helps, or not really?
Yes. So I actually didn't put this. We actually have a picture in the figure. I'll show you later. So the size of the Gaussians, if you constrict them to be too small, you're not going to get a good reconstruction. You actually get something that kind of, you get something blobby, very clearly blobby. And we have a whole range of them that we show in the paper, you know, how it changes. Ideally, you actually want to let Gaussians be as big as they want, because let's say you're taking a portrait photography and the background is just flat. You actually could just represent that with a single Gaussian. And if you did, you would get depth for free, because then you know you parse the image correctly. But because we're running, I mean, we're learning this over time, and we have to kind of backpropagate for each one of these parameters. If we let the Gaussians be as big as they want, it costs us much more. So for practical reasons, we put a max size on them, but we let them go up to that max size. Does that answer your question? Yeah.
Okay. Great. So I think we can thank Shiry again.